So it's a pleasure today to have Yogesh Dahiya with us from Chennai, who will tell us about decision trees and randomness. Please.
Yeah. Thanks for inviting me to give seminar. So I'll talk about the role of randomness in decision tree size. So let me start by giving the problem setup. We are given some Boolean function, and we would like to find out succinct representation of that function as a decision tree. Okay, so before I define decision trees, there can be multiple ways to represent a Boolean function. For example, one can just give a truth table representation, or one can just give a circuit which computes your Boolean function. But for example, if you give a truth table representation, then it seems that you're doing a lot of extra waste work, because there could be a lot of structure in your function which you can avoid. For example, in truth table representation, you are giving 2 to the n number of entries, because you're telling on each input what your function value is, right? For example, on left, this is just an AND function, right? But again, we're defining it on 2 to the n many inputs. So our goal would be to find out a succinct representation of a Boolean function. And in circuit, if you give a circuit computing your Boolean function, then that is inherently a bottom-up approach of doing things. A top-down approach of doing things could be that you adaptively query variables until your function value is determined. For example, to compute an AND function, I can start by querying the first variable. The first variable comes out to be 0, I can just output 0. Otherwise, I can start querying the second variable and repeat the process. And if I find out that all the variables are 1, I can just output it. Right? So this way of doing top-down approach of doing things is what is known as a decision tree. Okay. More formally, a decision tree is just a binary tree. The internal nodes are labeled by variables, and the leaves are labeled by 0, 1. Okay, and evaluation on decision trees is done as follows. You start from the root node, and you traverse down to the leaf node. You query variables one at a time. If a variable comes out to be 0, you go left. If it comes out to be 1, you go right. And you do this process until you reach a leaf node. And ultimately, you output the label of the leaf node. Okay. So naturally, a decision tree corresponds to a Boolean function, right? And we say that a decision tree computes our function if on every input x, the evaluation of a decision tree is same as the evaluation of our function. Okay. So this is what a decision tree is. And now we would want to find the succinct representation of our Boolean function in terms of decision trees. Right? So first, we have to define what succinctness means, and there are these two complexity measures which everybody studies. One is the depth measure, another is the size measure. But the depth is the longest root to leaf path in a decision tree, and the size is the number of leaves in the decision tree. Here, depth is telling us in the worst case how many queries I'm going to make. Okay, and size in the sense is telling us how much space I need to store this decision tree. Okay, because you only have order, number of leaves, many things, right? And so order, size, number of space, you can store this strategy which represents your Boolean function. Also, the depth in this model of computation can be thought of as time, and size can be thought of as space. Okay. And now we can define complexity of a Boolean function in terms of decision tree. Now we can say we will look at all the decision tree which computes our function and choose the one which has the minimum depth, and that will be the depth complexity of our function. And similarly, one can define the size complexity, look at all the decision tree which computes your function and choose the one which has the minimum size, and that will be the size complexity of your function. Okay. Having defined these measures, I've given some examples. On the left, there is this parity example. You are querying all the variables one by one, and on the leaves, you have other function values. There's a trivial way of doing things. You're querying everything, and this trivial decision tree can compute anything, because you can just put a truth table on the leaves, because each root to leaf path corresponds to unique input. Okay, so this is a decision tree for parity, and depth is n and the size is 2 to the n, and you can argue that in case of parity, nothing clever could be done, because if even if one bit has not been queried, you are not sure about the function. On the right, you have decision tree for and, which we've already seen. And again, for and function also, one can see that the depth complexity for and function is n, and size complexity is just n plus 1. Yeah. So depth and size can vary a lot. Yeah. Not very surprising. And let me now introduce randomness in our model. Okay, so the decision tree that we have seen so far, we'll call them deterministic decision trees. And randomized decision tree will nothing be but a distribution over deterministic decision trees. Okay, and an evaluation on our randomized decision tree will be done as follows. You start by sampling a decision tree from your distribution, and then return the evaluation of the decision tree on your input. So that's how you evaluate your input on a randomized decision tree. So the output of the evaluation will be a random value, depends on the sampling process. And we say that a randomized decision tree computes a function. It's a standard definition for every input x. You should be correct. Your evaluation of a randomized decision tree should be correct with probability 1 minus epsilon if you're looking for error epsilon. And this should hold for every input. The depth of a randomized decision tree is the worst case depth. I mean, you look at all the trees in your support, and the worst case depth among all the decision tree in your support is the depth of a randomized decision tree. And similarly, the size of a randomized decision tree is, look at all the decision tree in your support and choose the maximum size. So that's a size complexity, randomized size of your decision tree. And now again, we can do the same exercise. We can define the randomized complexity of our Boolean function, and using randomized decision tree, we'll say we'll look at all decision tree which completes our function with certain error, and choose the one which has minimum randomized depth. Okay, and that will be the randomized depth complexity. Similarly, randomized size complexity can be defined. And at this point, one can have these very natural questions. One can ask, what is the relationship? Is there any relationship between randomized depth and the deterministic depth? Is there a relationship between randomized size and the deterministic size? And the answer to the first question was given by the celebrated work of Nisan, where Nisan showed that deterministic depth and randomized depth are cubically related. Okay. So if you have a lower bound on the deterministic depth, then up to polynomial, you have essentially a good lower bound for the randomized depth as well. And very recently in stock, Ambani's, Belows, sometimes Montrose, they showed a function where the separation was at least quadratic. So the function whose deterministic vary complexity is at least randomized depth vary complexity to the power 2. So this 3 in the relation cannot be brought down below 2. Okay. And still we don't know what is the exact relationship between the deterministic depth and the randomized depth. We know that it should be somewhere between 2 and 3, but the exact constant is still unknown. And this is the status for 90s. Okay. So let me say how Nisan showed this result. To be instructive for this. The way Nisan showed this result was first, he characterized the deterministic depth using a combinatorial measure, which is block sensitivity. I define block sensitivity soon, but just think of ds of f as some combinatorial measure. What Nisan did was that he showed the deterministic depth complexity is polynomially related to block sensitivity. It is lower bounded by block sensitivity, and it is upper bounded by block sensitivity to the power 3. So he had this proxy, which up to polynomial loss characterized deterministic depth for us. Okay. The only thing then he needed to do was to show that block sensitivity is also a lower bound on the randomized. Okay, and that's what he did. He showed that block sensitivity is also a lower bound on the randomized depth, and that's how he got his cubic relation. So let me define what sensitivity is. For a function at an input x, we say that the bit I is sensitive if by flipping the ith bit, the function value changes. Okay, such a bit will be sensitive. For example, here we have an example. If we flip the first bit, function value is not changing. If we are flipping the second bit, function value is changing. So second bit is sensitive, the third bit is sensitive, and the fifth bit is sensitive. Okay. So that's how you define sensitivity. It's like if you're standing at a point and you have these n different neighbors, how many neighbors have different function values? Okay. And sensitivity at input is number of bits which are sensitive at input, and then the sensitivity of function is maximum over all inputs. Okay. And I'll use this notation, which is like you're flipping the bits of x in the position dictated by the set B. Okay, so x parity with 1b means that you are flipping the bits of x at the location that the location are determined by the set B. Okay. And in the case of block sensitivity, we say a block is sensitive if you flip the positions in that block at your particular input and the function value changes, then we say that the block is sensitive. Okay, now we are moving from one bit to a set of bits, and we say that block is sensitive, the function value changes. For example, in this case, the second and fifth bit, if you flip them, the function value changes. So 2 and 5 will become a sensitive block. Okay. And then the block sensitivity at an input will be the maximum k such that I can find k disjoint sensitive block at my input. So disjoint is important here. I mean, your sensitive block must be disjoint. And the block sensitivity of a function is just maximum of all inputs. You find the block sensitivity at each input and choose the maximum. I mean, in this case, we can think that we are standing at a point and we are changing some bits. So, and we are looking for disjoint directions, right? And so, in some sense, these we are not going one step forward, but we are going in like some vector direction. But these vectors are somehow independent because the blocks are disjoint. So their support is completely disjoint. So you are finding k disjoint directions in which you can go where the function value changes. Okay. And here are some examples. For example, in case of AND function, if you look at all the one input, if you flip any bit of all the one input, you'll get a 0 input, right? So every bit of one input is sensitive. So even sensitivity of an AND function is n. Okay. And similarly for majority, if you look at half of the bits are 1, half of the bits are 0, and now if you flip any 1 to 0, your majority won't be there, and the function value will change, right? So in case of majority, again, sensitivity is n value, and our sensitivity is always a smaller measure than the block sensitivity, because you can always choose one size blocks. Okay. So yeah, so going back to what Nisan did. So this is the block sensitivity measure, and what Nisan showed was that this is polynomially related to deterministic depth complexity, and also this tells us that randomized depth complexity is also large. Now I just want to make this observation. This probably people must have seen other cases. Let me define these two promise problem. There is promise OR, which is just an OR on the Hamming weight 0 and Hamming weight 1, and let's say and the promise AND is a AND function, but our input is restricted to just Hamming weight n-1 and n. Okay, so they have to behave like the AND function on Hamming weight n-1 and n, and on the rest of the inputs they can do whatever they want to do. So this is just a substructure of an AND function, and what we have seen, and we can see that if a block sensitivity of some function is large, then it essentially tells us that we can embed a large promise OR or a promise AND in our function. Okay, and this is just associating variable with each blocks, and then you can transform your function to a function which looks like promise code or promise and to changing of renaming the variables. So it's a very satisfying picture in that sense, because what this tells us is that if you want to prove a randomized query lower bounds, then you just go and look for promise or promise and type of structure inside your problem. Because if the problem is going to be hard, then it's going to be there. If such a structure is going to be there, then the problem is going to be hard, because it characterizes the randomized query. Now, let me come to the other measure which we were talking about. This other measure is a size measure. What can we say about size, right? Can we show similar relationship for size as well? Can we show that they are polynomially related? Even let's say I allow like polynomial factors also in my relationship, which essentially says that I only care about functions whose randomized size is super polynomial. I mean, I only care about polynomial relation. The randomized size of a function is super polynomial. Even such relaxation can we prove such results. And as it turns out, this relationship does not hold. And there is this example which people might have seen in other contexts. This is a function which is defined using a monotone formula of log n depth, where you have these alternating OR and AND gates. And for this function, very early work of Snare showed that the deterministic size of this function is equal to omega n. And there's a result by Sachs and Wigderson in Fox of 86, which showed that the depth complexity of this function is n to the 0.75, which tells us that the size complexity is like 2 to the order n to the 0.75. Okay, so the deterministic size is 2 to the omega n. The randomized size is just 2 to the order n to the 0.75. So there is an exponential separation between deterministic size and the randomized size. Okay. But if you look carefully on the log scale, things still look polynomial, right? I mean, there is a gap for sure, but on log scale, it looks like things are still polynomial, and that's the question that we asked. That can the log d size be related to log r size to polynomial mass? And this question was asked by Corneliuson, Mande, and Patro in FSTCS 2 as well. And this is our main theorem. So indeed, this is the case. Log of deterministic size can be upper bounded by log of randomized size to the power 4. And there are some polylog factors as well. So I will say more on polylog factors later on, but for now, let's ignore that. So there is this quartic relation between log of deterministic size and log of randomized size. So what this tells us is that if your deterministic size is, let's say, 2 to the omega root n, then your randomized size has to be like 2 to the omega n to the 1/8, for example. Okay. So it cannot be too small. It's like 2 to the omega root n, it cannot be like suddenly be polynomial or something like that. And to say more on this result, let me define the corresponding combinatorial measures to which we ended up showing this result. And one of the combinatorial notion is this notion of block number. Till now we saw the definition of a block which was sensitive. Now we say a block is minimally sensitive for a function at input x if that block is sensitive and no subset of that block is sensitive. Okay, so it should be the minimal block which is sensitive. Okay, so minimality is important. And then at an input, you collect all the minimal sensitive blocks. Okay, And the number of minimal sensitive block at input is the block number of a function at that particular input. And now again, we can define the block number of a function as maximum block number, if you look at all the inputs. So when we define this notion, but later on we realize that this notion has also appeared in earlier work of Petrianis and later in work of Kulkarni and Tal, but in different contexts. They were not looking at size measure. And actually it's surprising that nobody looked at size measure. Good for us. But yeah.
So the point here is that this will obviously be at least I mean, you can always just look at the block sensitivity and then minimize every block, but you can get a much larger number if somehow there are lots of ways of stacking up different blocks in block sensitive ways.
So let me make this point also clear that in block sensitivity, we force that the block should be disjoint, that the blocks need not be disjoint, they just need to be minimal. For example, in case of majority at all zero input, if you flip any set of n by 2 bits, you'll get a 1 input. That's a minimal block as well, because if you flip less than n by 2 bits, you're still going to be a 0 input. Right? So at all zero input, you have n choose n by 2 many minimal sensitive blocks. Right? But block sensitivity at zero input is only 2, because a block has to be of size n by 2. And you can only fit 2 disjoint sensitive blocks at all zero input. Okay, so you're allowed to be, not be disjoint now, but you have to be minimal, and this minimality will play a crucial role in showing up the size of blocks. The other interesting example which I would like to mention in case of block number is this parity example. In case of parity, every bit is sensitive. Every odd set of bits that also forms a sensitive block. But the minimal block are these sensitive bits only, one size blocks, right? So the block number of parity is just n, right? Every odd set of bits forms a sensitive block, but only the single bits are the minimal blocks at any input. So the block number of parity is just n. Yeah. The other notion, which I'll just state now, is the notion of cover number. Let me define the notion of subcube first. So subcube of codimension k is nothing but a partial assignment where you're fixing the k variables and the rest of the variables are all, can be anything. And we say that a subcube is monochromatic with respect to a function if every input which reside in my subcube has the same function. Okay. Yeah, and now we can define the cover number of our function. We say, oh, this is 2 to the n, many points are there. You cover them using subcubes, using monochromatic subcubes, and try to find out minimum number of subcubes which can cover the whole space. Minimum number of monochromatic subcubes which can cover the whole space. And that will be the cover number of our function. Okay. So it's the definition. It's clear that cover number lower bounds the deterministic size, because if you take any decision tree which computes a function, and if you take a root to leaf path, right, then this corresponds to a subcube, and it has to be a monochromatic subcube because this tree is computing your function. So the leaves corresponds to monochromatic subcubes. So the leaves of a decision tree which computes a function, the subcubes corresponding to those leaves gives you a cover number. Not just a cover number, it actually gives you a partition of your space. Not just a cover of your space using subcubes, but a partition of your space using monochromatic subcubes. Yeah, so it's interesting to ask, like, what's the relationship in the other direction? We know that cover number lower bounds are deterministic size. Can we say that cover number also upper bounds deterministic size instances? And there's an old result by Alphonse and Hausner which showed that log of deterministic size can be upper bounded by log of cover number to the power 2, and there is this log n factor also in the relation. And there exists a function where deterministic size has to be at least log square of the cover number, but it's still an open problem whether this log n should be there or not. So combining these two, what we get is that log cover number is a lower bound on log of deterministic size, and log of cover number to the power 2 into log n factor is an upper bound of deterministic size. So now we have a combinatorial measure which can act as a proxy to log of deterministic size, right? If only somehow we can show that log cover number can also give us a lower bound on of randomized size, then our relationship will complete. So the question now is, can we show that log of cover number is large? If the cover number is large, can we show that log of randomized size is large? Okay. And that's exactly what we've shown. We show that log of cover number to the power 1 by 2 is a lower bound of on the log of randomized size. Okay, and we prove this thing in two steps. Where in one step we say that if the block number is large, then definitely your log of randomized size is going to be large. Okay, but in the other direction, it is not true. If your log of block number is small, then you cannot say that log of randomized size is small, because we just saw an example. Parity was an example where log of block number was just log n, right? Because your block number was just n. But it's not hard to argue that randomized size for the parity should also be like 2 to the omega n. So in the other direction, it fails miserably. We can only show that if the log of block number is large, then the log of randomized size is large. But if log of block number is small, then we cannot say that log of randomized size is small. So in that case, we say, okay, let's say block number is small, and additionally, log of randomized size is also small. Randomized size is also small. And combining these two facts, we can build a cover. Okay. So if the block number is small, log of randomized size is small, then combining these two information, we can build an efficient cover for our function. And now combining these two steps, log of randomized size, log of block number can be upper bounded by log of randomized size. You get that log of cover number is upper bounded by log of randomized size to the cover. Tilde is hiding log n factors. Log n factors. There's polylog factors.
So in both you have tildes?
Yep, in both have tildes.
So in one you have logs from the front.
Yes, so that's why it's
so log n, log n, log n.
So now we can first apply the Herenthofen-Hausler result to go to log square of cover number, and then we can apply this cover theorem to go to log of randomized size to the power 4, and there will be 3 log n's as I pointed out. Okay. Yeah, I'll say more on this in the second half, and so let me move on to other consequences of our size theorems. So we started studying more generalized decision trees, where instead of just variable queries, you are allowed to make more general queries. Okay, let's say you have some class of functions, and you're allowed to ask. You can choose a function from that class, and you can ask a query. You can test whether that function has 0 or 1 on your input. So we just saw that in case of ordinary decision tree, something is not for ordinary randomized decision tree if it embeds promise or promise and, right? So it's very natural to extend the ordinary decision tree by saying that, oh, I'll add the power of or in my decision tree, but I'll add the power of and in my decision tree. Okay. So So the two natural decision tree which one can study is like AND decision tree, where you're allowed to make AND queries, where AND query is just, you take AND of subset of variables. And OR decision tree is where you're allowed to take AND of subset of variable or OR of subset of variables. Okay. Yeah, so this is AND decision tree, and again you can ask, role does randomness play in such decision trees? Okay. Another interesting case one can study in this generalized setting is parity decision tree, for which we don't know a lot, much. For example, one interesting question is that this Aaron-Foster type result is not known for parity decision tree. Let's say you want to cover your space using affine spaces, and can you show that the parity decision tree size, log of parity decision tree size is upper bounded by log of cover number using affine space, because affine space will make sense in the parity case. And the other interesting generalized decision tree is the linear decision tree, for which also we don't know. So yeah, again, so we can ask these questions: what is the role of randomness in AND decision trees? And this question was asked by logarithm and Yuan, in a survey in SICOMP, where they conjectured that this randomized and deterministic depth complexity in AND decision tree must be polynomial. Okay, and the way they came to this question was they were looking at log rank conjecture for AND functions. There are AND function is you have an outer function and you compose that with 2-bit AND. And for that class of function, you want to show that log rank conjecture is true. And they showed that that is the case up to log n factors. Another interesting case in this direction is XOR functions. Take a function, compose it with 2-bit XOR, and you ask the question: can we show that log rank conjecture is true for this class? We don't know, and the reason we don't know is because we don't know much about parity decision trees. And that is the reason. And so this question actually, in the paper, you'll see that this question was nothing but a question about AND decision trees. So they started studying AND decision tree, and finally they conjectured these. They made several conjectures about AND decision tree, and one of the conjecture was this: that can we show that a randomized AND decision tree complexity is same as deterministic AND decision tree complexity? And indeed, this is the case. We show that even over here, things are cubically related. Okay. And the high-level idea for this result, I mean, so this measure MF, just think of this measure captures how big OR can you embed inside your function. Okay. So what this first relationship is saying is that if you can embed a large OR, then your randomized AND decision tree, then the randomized AND decision tree complexity must be large. Because OR function is hard for AND decision tree. Okay. By making this AND queries, it cannot come to OR function. We can fool it because we can keep answering 0, 0, 0 to AND queries, and I can do this n-1 times and don't know much in the deterministic case, and then in the randomized case, we can build a suitable distribution of it. So if there is an OR setting, then obviously randomized AND decision tree complexity is large. But then there are other functions which are hard for randomized AND decision trees, where we cannot embed large OR inside your problem. So the other important thing is we show that if the cover number is large, then you can prove that the randomized AND decision tree complexity is large. And in the other direction, we showed Aaron-Foster type result where we say that if you cannot embed a large OR inside the function and your cover number is also small, then the deterministic AND complexity is going to be small. Okay. yeah, as I said, OR is hard for and decision trees, and right, and cover number. So one thing I want to say at this point, so if there is an AND decision tree of depth D, right, you can convert that into a, yeah.
So Hausler and I don't know how to say his name. They work in machine like learning field.
Yeah.
And this M in the machine learning side is called the hollow star number. This is the way it's so there is some analogy between things related to dimensions on the machine learning side or the learning side and this type of
I'm not aware of that literature. There might be some connection.
yes, so maybe you are aware of their paper.
Mhm.
Hausler, you mentioned
Hausler, we were
Yeah.
aware of, yeah.
Yeah.
Oh, Hausler, I did it.
Hausler, like their paper is incorrect, which
Yeah.
means that it's related
The
to
learning theory.
yeah.
I mean, they say because the cover number is just saying you have a DNF and a CNF for your function, and for such function they were trying to back learn such function, but the cover number is not,
Mhm.
where you can construct a DNF and CNF for the function.
So this M is called the hollow star number. This is how it's the name in this literature. So
Okay.
maybe it's worth trying to see.
Yeah, I mean, I didn't define this properly because I don't want to define it, but this is just in rough sense. This says that you can embed a large R inside your function. Yeah, so I was trying to make this point that if you have an AND decision tree of depth tree, right, you can convert it into an ordinary decision tree of size n to the d, right? Because just open up the queries, open up each AND queries, and you incur a factor of n each time, and you will get an ordinary decision tree of size n to the d. Because what we'll do is we'll invoke a size theorem here. Because what we have is that AND decision tree complexity is upper bounded by this measure MF and log of cover number. And the MF essentially says that R is sitting there, so the randomized AND decision tree has to be large. And the log of cover number, we can use our size theorem to upper bounded by log of R size to the power 2. And if size is large, then the AND depth has to be large. Because if AND depth is D, then the size has to be like n to the d. So again, a log n will come, which I'm hiding. Okay, so the size is large and the AND depth is to be large. Because if AND depth is small, then size is small. Syntactically, because you can open up this space. So this again, I mean, this comes essentially uses this fact that you can connect cover numbers in the randomness. Okay. So AND seems very handicapped, right? We cannot even do OR. So let's add OR also to the mix. Now we can ask AND queries and OR queries. Okay. And again, we can ask the relationship, what role does randomness play in such query model? And what we show is that it's the relationship is again polynomial up to just hiding everywhere logins.
I was wondering where the logs were.
They will come afterwards. Let's say something about that. But this actually is the same question as size question, because if you allow AND queries and OR queries, you can balance your decision tree, right? Because if you have a decision tree, then you can find a node which has like more than L by 3 many things and less than 2 L by 3 many things, and L is the number of leaves. You can find this node and you want to now test whether I can reach this node. But to test, you have to test some variables. You have to check that these are 1, and some variables you have to check that these are 0. But all the variables which are set to 1, you can check them by making just one AND query, and all the variables which are 0, you can test them by making one OR query and seeing if it comes up to be 0 or not. So you can test whether you go to that balanced node by making one AND query and one OR query. And so you can convert a S size ordinary decision tree into a AND OR decision tree of depth order log S. And so this is very syntactic. So this holds for even the deterministic setting and in the randomized setting also, because you can do this operation on each of your decision trees that is being ruled. So this essentially is the randomized AND OR query complexity is nothing but theta of the log of randomized size, and the deterministic AND OR query complexity is nothing but theta of log of deterministic size, and these two quantities we already know have a relationship. So here also we have the same relationship. So I'll say something about necessity of factors. So everywhere we have log factors. So in these two theorems, we have a counter example that says that we cannot avoid the dependence on log n, because if you consider this threshold of n-1, one can show that deterministic AND OR query complexity for threshold of n-1 is theta of log n. So to make log n number of queries by an adversary argument, it's an easy exercise, and you can randomize AND query complexity of threshold of n-1 is just order 1, right? Because you can choose a random set of bits, and you can compute AND of that and AND of rest of the bits. If both comes out to be 0, you have 2 zeros, right? And so this will separate, if there are 2 zeros, this will separate them into the 2 separate sets. And so with the probability half, you will detect whether threshold of n-1 is there or not. And you can repeat a couple of times. So randomized AND decision tree complexity of the threshold of n-1 is order 1. So this tells us that, I mean, some dependence on n must be there. And about the size theorem, we can get rid of this log n because let's say your function depends on all n variables, and it's without loss of generality because we can always reduce and start with an n such that your function depends on all n variables. For such function, you can show that randomized size has to be omega n. Okay. It's not a very hard exercise because you can build a non-adaptive decision tree starting from your randomized decision tree, and then say that clearly non-adaptive decision tree must have omega n size. Okay. So what this says is that now you can bound this log n, upper bound this log n by log of randomized size, and you can get a polynomial relationship between log of deterministic size and log of randomized size. So it's much worse. Yeah. Okay. So what about separation? Like, how good are these results? Like, can we say how good is this 4? Can we bring it down to 2, less than 2, 3, whatever? And separation between log D size and log R size is at least as large as separation between deterministic depth and the randomized depth. And this was first pointed out to us by John. And there is a very simple lifting argument for this. Let's take a function and compose it with 2-bit XOR. Deterministic size of that function, then log of that will be at least depth, right? This is like saying we can lift depth to size and tree-like resolution to, and the log of randomized size of F composite XOR can be upper bounded by the randomized depth, because you can start with tree which computes your F, can simulate that. Whenever you're computing a variable of F, you can extend that out and compute the two variable corresponding to XOR. So that will blow up the size by a factor of 4 each time to make a query. And since the depth is D, your size will be like 4 to the D. So on log scale, you will have order randomized depth is an upper bound on log of randomized size of F composite XOR. So what this tells us is that the separation between log D size and log R size must be at least as large as separation between deterministic depth and the randomized depth. And we already know that the separation between depths is at least quadratic. So this thing can come down to 2, not be. And same thing can be said for AND decision tree also. I mean, the same separation in a black box way. If the separation improves in the depth, the separation will improve here as well. There's a quadratic separation in the AND case also. Again, when some small gadget lifting one can do. Again, so this 3 cannot go below 2. And moreover, we can show that this result of ours is a generalization of Nisan's result, because starting with our result, we can derive Nisan's result by doing this clever lifting with XORs. We start with deterministic depth, that is a lower bound on log of deterministic size of F composite XOR. And then we saw that how size log of D size is a lower bound on depth of AND decision trees. And then from deterministic AND, we can go to randomized AND using R relation. And then this is just saying you take a function which take a tree which computes your F and simulate that. And whenever you make a query corresponding to F, you make 2 queries corresponding to XOR. So your depth only increases by 2. So it's a factor of 2. Will make almost a factor of 2. But you end up relating deterministic depth with randomized depth. So in that sense, it's a kind of a generalization of Nisan's method. So it will be, if you improve this 3 below 3, then you'll end up improving Nisan's result, which has not been improved since then. Okay, so let me summarize this now. So we showed a size theorem where we proved that the log of deterministic size is polynomially related to log of randomized size. Okay, and en route to proving this, we showed that if you can show that cover number of your function is large, then that can translate to proving the randomized size limit. Okay. And then we looked at 2 different models, more generalized decision tree. We looked at AND/OR decision tree, and there also we saw that deterministic AND and randomized AND/OR complexity are polynomially related. And the same is the case for AND decision tree. I guess next question. Thanks.
Questions? Did you have any conjecture about parity decision trees?
Shahar has a lot of conjecture about parity decision tree in this survey, in the SICOMP survey that I mentioned.
Okay.
And one of the problem I told you is like, is this Hausler type result for parity decision trees? And then this cover theorem type result also. If you can say the parity cover, your function is large, which is like saying it can cover things. If you need like a lot of affine spaces to cover your space, then can you show that the randomized parity decision tree complexity is large? Okay, we proved it for ordinary decision tree, but this conjecture is stated. exactly in his survey, and the corresponding result for parity decision in second bullet. And Hausler result is also known for parity decision tree. I mean, a lot of things in parity decision tree. And in this, another interesting question which I didn't mention over here, which Shah is very much interested, was looking at, you can look at polynomial representation of a function over 0-1 basis, where your monomials are there, not over plus minus 1, not over Fourier, over 0-1. And he has this another conjecture which says that approximate sparsity can be shown that log of approximate sparsity and log of sparsity are polynomial related. So that's one very good, interesting open problem that one can think about, and a lot of problems in parity.
So basically, you're saying I should write my function as a multilinear polynomial, and then I'm looking
Yes, yes, and then you count the number of monomials, and that is the sparsity of your function. And in the approximate sense, you're saying you can, if it's 1, then you have to be more than 1 minus epsilon. If it's 0, the function must evaluate to less than epsilon, and that's the approximate representation of your function. And
so these are like probabilistic polynomials?
no, it's not probabilistic, it's approximate polynomial. It will not give you it need not give you a 1 on a 1 input, but it should give you a value which is, let's say, more than 2/3.
Okay.
On 0, it should give you a value which is less than 1.
Okay.
And you can look at such polynomials for your functions. And then again, you can define sparsity. And the question is the approximate sparsity, log of approximate sparsity, same as log of sparsity of the polynomials? Very interesting. In fact, if you prove that conjecture, then this AND decision tree, this result will fall. Because we can lower bound AND query complexity by log of sparsity, and we can lower bound randomized AND decision tree also by log of approximate sparsity. So if you can relate those two, then we'll end up getting this for free. But the other way is not free.
Any other questions?
Maybe we will go into the details about this, but maybe we'll give it a quick answer. How much of the facts about polynomials, for example, approximating 0-1 polynomials, do you actually use in this?
None.
No.
Cool. I guess that's the reason. I guess Shah was working with this algebraic notions, and we're lucky enough to look at combinatorial things and get this result out. Probably the algebraic setting is more difficult, but in our proof we just work with combinatorial setting.
Okay, so then let's take a break.
So we are back after the break and are going to open the hood and hear about some of the technical details. Please.
So I'll tell you about the main theorem, which was about size. So I'll give you the whole proof essentially, because it's a simple but a neat proof. And because I think we had the right combinatorial measures to make everything work. That's why it came out to be very neat. Okay. So as we saw that this theorem is proved in these 2 steps, where one of the steps is we say that if this block number is large, then we can show that the random size is large. And the other step is that if we show that the block number is small and the randomized size is small, then we can extract a small cover out of it. And if we can extract a small cover out of it, then we can use Ehrenfrost and Hausler result to build a decision tree out of it. Okay. So we can, starting from the randomized tree, we can come to deterministic tree. Okay. So essentially, I have to show you these 2 levels. So we'll begin. It will be instructive to revisit Nisan's result because of those ideas will come in. So I'll just quickly do that. What Nisan showed was that block sensitivity is a lower bound in the randomized query complexity. Before we see that, I guess it's obvious that sensitivity will be a lower bound on deterministic depth, because let's say there's an input with the S many sensitive bits, and let's take any tree which computes your function, and on this input, let's take root to leaf path, and if this root to leaf path, if the variables which are queried on this root to leaf path does not query a variable which was sensitive at input X, then you cannot distinguish between X and X with the ith bit flipped, right? Because they both will take the same path. But since ith bit was sensitive, the function value was different. Right? So the root to leaf path must query all the sensitive bits. Yeah. It's a fitting type statement which says that must query all the sensitive bits. And essentially, the same thing will work for block sensitivity also. Why? Because now we can say that a root to leaf path must hit every sensitive block, right? Because if it miss some sensitive block, then we will not be able to distinguish between X and X with block leaf left, right? So essentially, this will form a hitting set for all the sensitive blocks, the root to leaf path, the variables queried there. Okay. And since in case of block sensitivity, we can find k disjoint blocks. To hit k disjoint blocks, you have to have at least k variables. So root to leaf path must have space k, where k is a block sensitivity. And now we can go to the randomized setting. Okay, that's what we want. And essentially, we can have a same hitting set type lemma. Where we say if we have an input X, earlier we were saying if we take a root to leaf path in our decision tree, then for a sensitive block B, at least some variable from that sensitive block must be good. Here we'll say at least some variable from a sensitive block must be queried with good probability, with probability 1 minus epsilon. Take any input X, take any sensitive block for that input X. A randomized decision tree must query some bit from that block with probability 1 minus epsilon. And the proofs write itself. Essentially, what this is saying is, let's say by contradiction, this is not the case. By that, we mean that no bit of D is queried by the randomized randomized decision tree on input X with probability more than 2 epsilon. Right? The probability more than 2 epsilon, no bit of D is queried. That means that on X, that the randomized decision tree is not able to distinguish between X and X with the bits in D flipped with probability more than 2 epsilon, which means that it has to be incorrect with probability at least epsilon either on X or on X with bits in D flipped. That's essentially what this is saying. If it's if we are not querying any bit of D with probability more than 2 epsilon, and the randomized decision tree will not be able to distinguish X and X with bits in D flipped with probability more than 2 epsilon, which means there are these 2 epsilon masses spread over these trees, and on X and Y they'll take the same path, and so either they will be correct for X or they will be correct for Y. So either we'll have error of more than epsilon on X or more than epsilon on Y. So this tells us that for input X and a sensitive block B, the randomized decision tree must query at least some bit from B with probability at least 1 minus 2 epsilon. Yeah. That's a noisy hitting. And now we can prove the block sensitivity lower bound, right? Because there exists an input which has k disjoint blocks. On expectation, each block, some bit from that must be queried with probability 1 minus 2 epsilon. Right? And since these blocks are disjoint, on expectation, I must make block sensitivity into 1 minus 2 epsilon many queries. because there are S disjoint blocks with probability 1 minus 2 epsilon, you will end up querying some bit from each block. On expectation, you are making S into 1 minus 2 epsilon many queries, and which means that there must exist one decision tree in your support where you have that many queries. Okay. So this proves that the block sensitivity is over one on the randomized depth. Okay, so now let's come to the proof. We'll start with dilemma 2. Okay. So we want to show that the block number is a lower bound on the randomized size. And let's start by the easier claim. Let's first show that the block number is a lower bound on a deterministic size. And this is, so let's start with some decision tree which computes our function. And let's choose the input which achieves the block number. And let's say there are k minimally disjoint blocks at that input. And let those blocks be B1, B2 to Bk. And consider following inputs. Take your input X and flip these sensitive blocks. These are these k inputs. Now my claim is that all these input must go to distinct leaves. And that's essentially because of minimality. There are two observations to make. Since these blocks were minimal, right? You take X and you flip a minimal sensitive block, you get to a Y input, right? And on Y input, every bit from B will be sensitive, right? Because the flipping a bit of B in Y is equivalent to flipping, size of B minus 1 bits on X. And since the block was minimally sensitive, it essentially means that every bit on Yi, every bit inside Bi will be sensitive. Is this point clear? Because it's minimal. So we have this input X. Let's say there is some block Bi, and we are defining this point Yi where this block is flipped. Okay. Now, if I flip a bit from this block, I'll get to an input which can also be obtained by flipping, leave this bit and flip the rest of the bits. But since no subset of this block is sensitive because it is minimally sensitive, so this will have same function value as X, and Y has a different function value. Okay. So for each Yi, every bit in Bi is sensitive. Let's come to the observation 2. Now, these blocks are minimally sensitive. They form an anti-chain. No one is contained in other. Right? So if you look at any two blocks, there exists a coordinate which is there in Bi, which is not there in Bj. And other way around also, there exists a coordinate in Bj, which is not in Bi. So this observation is also obvious. So since every bit of Bi is sensitive at Yi, if you take a decision tree which computes a function, then on input Yi, it must query every bit of Bi. Right? It cannot miss because of our fitting argument that we saw. So for Yi, it will query every bit from Bi. For Yj, it will query every bit from Bj. And now they must go to distinct leaves, right? Because there exists a coordinate which is there in Bi, which is not there in Bj. So Yj cannot trace the same path because Yj is same as X on that coordinate, right? So they will diverge at that point. So they will end up going to different leaves. And it's the proof because what we have constructed is this block number many inputs, and each of them are going to distinct leaves. So the size is at least the block number. Now let's come to proving by block number also imply lower bound on the randomized size. And so essentially we'll say, okay, we have constructed these k inputs corresponding to these minimally sensitive blocks. In the deterministic setting, each of them were going to distinct leaves. But in the randomized setting, we'll say a constant fraction will end up going to different leaves on expectation. And then that means that there exists some tree in my distribution where constant fraction of these yi's are going to distinct leaves. So that's the idea in this. So we'll start. I mean, this simplifies the whole proof. We'll start with the decision tree whose error parameter is 1 by 2n, not 1/3, 1 by 2n. And size of such a decision tree will be like size with error 1/3 to the order log n. Because you can boost the success probability, you can from 1/3, you can come to epsilon success probability by repeating log 1 by epsilon many times and taking the majority. Right. So we'll work with the error parameter 1 by 2n and show that show the lower bound on this size. Okay. And that would imply our result, because if I prove that this size is like omega of block number, then if you take log both sides, you'll get log of block number is upper bounded by log of R size into log n. So essentially, if I just prove that this size with error parameter 1 by 2n is lower bounded by block number or some constant fraction of block number, then I'll be done. Same thing, let's define these yi's. And as I said, he'll argue that constant fraction of them will go to distinct leaves on expectation. That's our idea. So in the deterministic setting, we were saying or deterministic tree cannot miss any bit from bi on the input by i. Okay. In the randomized setting, we can say the error probability is like 1 by 2n. Then with probability 1/2 is it must vary every bit of bi. Why is that the case? Since each bit is sensitive by noisy hitting lemma, that bit must be queried with probability at least 1 minus 2 epsilon. Because we saw that if there is an input and there is a sensitive block, then some bit from that sensitive block must be queried with probability at least 1 minus 2 epsilon. Here, this bit itself is a sensitive block. Each bit in bi is a sensitive block. And so that bit must be queried with probability 1 minus 2 epsilon. Right? So the probability of this not happening is less than 2 epsilon. And the size of this block can be at most n. So by union bound, the probability that I don't query all the bits of bi on input by bi is size of bi into 2 epsilon. And that is, since our epsilon parameter is set that way, is 1 by 2n. Of bi can be at most n, and epsilon is like 1 by 2n. We get that with probability at least half. All the bits of bi must be queried on input by sub bi. Is this clear? Yeah. And now, we can just run the expectation argument. You are saying on y1 or by b1 with probability 1/2, all the bits of bi will be queried. Same for other y sub bi's. So on expectation, on half of them, all the bits of their corresponding b's will be queried. And if all the bits of b's will be queried, then those input must go to distinct leaves because of minimality that we saw earlier. Right. So on expectation, half of these bi's, the randomized decision tree must query all bits of bi's for half of them. Right. And that means that on expectation, half of these sub bi's must go to distinct leaves. And that means that there exists some decision tree in the support of this randomized decision tree with error parameter 1 by 2n. There all these bi's are going to distinct leaves, so size will be at least half the block number. And then that's the end of the argument. Yeah. So this shows that if the block number is like large, then you can do randomized size overloads. And essentially, we started with the example of majority, and we're like, can we find an argument for majority? Randomized size of majority is large, and then we came up with this distribution where we were saying okay, this distribution is, you take all 0 input and you flip the n by 2 bits, and you come to this middle layer where we have these n choose n by 2 in inputs, and now these are the hard inputs, which makes randomized size large. And then one can generalize this and say we have to look at these minimal blocks. And that's how you end up discovering that this block number, if this number is large, then we can show randomized size numbers. Okay, let's come to the other direction. So the other direction says that if the block number is small and the randomized size is small, then we can build a small cover. Every step will be elementary, but it gives something interesting, it seems. Let me make some observation. This is with this W, I'm collecting all the minimal sensitive block at input X. It's a notation. And I say that H hits this family of sets if it contain at least one variable from set. And by this notation, I'm just saying that you take an input A and you fix the bits which are described by the set H, and this will denote the subcube that you will get for doing that operation. This is just a notation. I'm just guessing. This is just a subcube where you are fixing the bits mentioned by H, and the other bits according to H, and the other bits are free. Just a notation. And I guess it's clear because what this proposition is saying that if you find a hitting set for all minimally sensitive blocks, then that hitting set is essentially a certificate for your function value, right? It determines your function value. If you reveal your input on those locations, your function value is essentially pinned down.
Now X is this concrete. X is now the input that we're looking at, right?
Correct. This should be A.
And you've now looked at all the possible blocks that could flip to the opposite value from X, but you picked up a bit that is wrong in all of these.
Correct. We are correcting all the minimal sensitive blocks, which if we hit minimal sensitive blocks, we hit all the blocks, right? And if we hit all the sensitive blocks, then essentially we are creating a certificate for that function at that particular input. Because you cannot, the subcube defined by fixing your input on those locations will be monochromatic. Because if it's not monochromatic, then let's say there exists some other input with different label, and this X and Y will differ in a set of bits which is not hit by your hitting set, and that is a sensitive block. So it must have been hit by your hitting set. So it cannot happen. So this hitting set in the subcube for your input to define using the hitting set will be a monochromatic subcube. Essentially, what this says is that if for input, if you create a hitting set for that input, by hitting set I mean you hit all the sensitive blocks at that input, then that will give us a monochromatic subcube containing that input. Let's come to the proof now. Again, I think it's a neat technique because earlier we had this combinatorial proof where we were not working with small errors, but then we had to do other things. And then we realized we'll do work with small errors and then boost simplify the analysis a lot. So again, here we'll work with error, which is like 1/4 the block number. And again, this is true. You can start with 1/3 error and bring it down to 1 by block number by repeating block number many times. And now essentially, if I can show that this, if I start with this randomized decision tree for this error, and assuming that the block number is small, I want to construct a cover for it. Okay. Okay. So again, if you take a randomized decision tree for an input X, we saw that a sensitive block must be hit with probability 1 minus 2 epsilon. Right. So what is the probability that you hit every minimal sensitive block? Right. The probability that you miss some sensitive block is at most 2 epsilon times the number of minimal sensitive blocks, which is bounded by block number. So the probability that you miss some sensitive block, you don't hit some sensitive block while doing this evaluation, is at most 2 epsilon times the block number. Since epsilon is like 1/4 the block, 1/4 the block number, you miss a sensitive block with probability at most 1/2, which tells us that with probability 1/2, you're going to query at least 1 bit from each sensitive block. In your randomized decision tree, the error parameter is 1 by block number, right? But if you hit each sensitive block, right, you're essentially creating a certificate. So the leaf corresponding to that and the subcube corresponding to that will be a monochromatic subcube. Right. So what this says is that the probability at least 1/2 the set of variables queried by the randomized decision tree will form a monochromatic subcube containing your input. Okay. Okay. And for one input, with probability 1/2, I'm able to cover that input. Okay. So let's take n independent copies of trees sampled from army. Then the probability 1 by 2 to the n the probability 1 minus 1 by 2 to the n for every input x, you'll have a subcube which covers that input. And then by union bound, you'll say that with non-zero probability for every input x, there will be some tree where if you trace root to leaf path, you'll end up in a subcube which is monochromatic and which contains that input. Is this clear? Yeah.
Can you say this just again? What is happening with this? For some reason I got lost. I'm not sure where I got lost. My question is a bit vague.
So what we are saying is that on an input x, with probability at least 1/2, will be able to hit every sensitive block.
Yeah, and this is because we boosted the accuracy
To 1 by block number.
really high.
And there are only block number many things we have to kill. And the probability that we don't kill a thing is less than 2 epsilon. So by union bound, with probability 1/2, I'll miss some block. With probability at least 1/2, I'll be able to hit every block. And once this is there, then I can say with probability at least 1/2, the set of variables queried by randomized decision tree will form a monochromatic subcube containing my input. Because if I hit every sensitive block, then I'm actually creating a certificate for that.
As I mean by the argument we had before.
Right. So with probability 1/2, I'm collecting a subcube which covers this input. Right. And now let's take n independent trees from my randomized decision tree.
Yes.
Just trying to boost things so that I can apply union bound. Right. Each of this tree will give me a monochromatic subcube which covers my input with probability 1/2. Probability that none of them gives me a monochromatic subcube which contains my input is less than 1/2 to the power n. Right. The probability of bad event, if I just now apply union bound over all inputs, is 2 to the n into something which is less than 1/2 to the n.
So just by rephrasing what you said, is just by union bounding, there has to be n trees that will
Correct.
cover all the.
Correct.
Mhm.
So there is a non-zero probability that there exist n trees in my support of R mu, such that for every input x, there exists some tree, such that if I evaluate my input on that tree, I'll end up in a monochromatic subcube. So those entries, if you look at the leaves of those entries and the subcubes corresponding to those leaves, a subset of them is going to form a cover for my whole space. Right. That's what it is written, which is in 9 probabilistic argument. And so what this says is that the cover number is at most n times the size of R mu, because every tree in my support has size at most size of, it's how size is defined as the maximum measure. It's n times size of R mu, and size of R mu is 1/3 error size to the power log of block number. Just take a log and recover lemma. Any questions?
So in this case, the filter is not a log n factor, but it's an additive like log n.
Yeah, it's you'll get additive log n. Right, not can multiply will only those things.
So this is saying that, okay, if the model is deterministic, then I simply take one tree and simply take the decision tree and take its leaves. That's a problem. And now we're saying that if the model is somewhat stronger, it's randomized computation, then it's not far away up to a log BSF magnitude as a multiplicative factor.
I mean, in case of randomized decision trees, your leaves of the trees,
They could
You know, support-
they could be imperfect.
they can be imperfect.
Yes.
But if you boost your error to such a small error, then suddenly you will start finding,
Oh, if I boost it, then suddenly there for some input apps, I can find a perfect lead
Correct.
for that app. And
Correct.
actually, those apps are meant for many
Correct. and then you collect entries to apply union bound so that you can collect for each of them. Yeah, I guess we can summarize. We have the size theorem which says that log of deterministic size is related to log of randomized size, and there's this intermediate result which is relating non-deterministic complexity to the randomized complexity. So this cover number can be thought of as deterministic size. And with some extra work, this is exactly the same question as size question in disguise, because we can do balancing when and or are allowed as queries. And for relating deterministic and randomized and with some more work and using the size theorem, one can even get this relation. And as I mentioned, this relation in some sense can be thought of as generalization of Nisan's result because you can recover Nisan's result starting from this result. So that's all I have. Yeah, thanks.
Any final questions or comments? Or protest?
Really?
And Niger somehow came out to be right that analysis.
Seems like the thing you'll teach, like, you can easily teach them courses for.
And so block number, is this like, has it, I guess maybe you said so and I forgot a
Yeah.
little, but has it been studied before? I mean, it's such a nice,
Yeah, it turned out it was studied before. And we were not aware of it, but somebody
but
told
somehow
us.
not so
In
much.
not so much, not so much. There's one paper that Medrian is on quantum query complexity in relationship with ordinary query complexity. There, he improved something using block number, and later on, Tal and what was there? Improved on Medrian's result using block number. So it has been applied in some circumstances, but not enough. It can find more application in context of size. But in some senses, it doesn't capture size because we had this example of parity, where parity had a very small block number, but randomized size of parity is to be omega. Right. So in that sense, it's not neat enough. Because in case of depth, we said the block sensitivity is all you need to know if you worry about randomized query. But here you cannot say the same thing. You have to look at cover number.
For monotone functions.
Right. For monotone function, this will be true. Yeah.
Is there clear? Is there anything clear that can say about the other number of
It's the number of minimum terms.
The min terms are actually
The mean term is
minimal sensitive blocks at all 0 input. So this relationship between cover number and log randomized size can be improved for monotone function. And this factor of 2 can be removed. So you'll get the log D size related to log R size with about 2, I guess, in case of monotone function.
Okay, thank you so much.